Inorganic Chemistry Crash Course. For today, we will be discussing chemical bond. So, now let's move on to Crash Course 5, Polarity and Intermolecular Forces. So, we will be discussing polarity and intermolecular forces of attraction. Okay, Gina guys? Gina! Let's go. So, we say that a molecule is polar when it has a net dipole or net dipole moment due to the net effect of its polar bonds. Now, what is a dipole? For example, we have hydrochloric acid. So hydrogen here has a partial positive charge, while chlorine has a partial negative charge. This is because chlorine is much more electronegative than hydrogen. So, meron silang electronegativity difference. Hence, the separation of the partial positive charge of hydrogen and the partial negative charge of chlorine creates a dipole, as shown by this red arrow. So, guys, CHCl is polar because it has a net dipole. Okay? Next, we have carbon dioxide molecule. Here, we see that the partial positive charge is oxycarbon. Tapos oxygen naman ang may partial negative charge. This is because mas electronegative si oxygen than carbon. Now, the dipole goes from the partial positive charge of carbon to the partial negative charge of oxygen. So, from left tapos pa right din, right? So, itong dalawang to. Now, these two dipoles will cancel each other out, making carbon dioxide non-polar. Okay? Ito ay dahil, guys, carbon dioxide, ano nga ba molecular geometry niya? It's linear. Now, linear molecular geometry is very symmetric. Meaning, pag symmetric, yung mga dipoles niya, pwedeng i-cancel. Okay? Because of that, carbon dioxide is non-polar. Next, we have the water molecule. Here we see that the partial positive charge is on hydrogen and the partial negative charge is on oxygen, since oxygen is more electronegative than hydrogen. So, the dipoles go from here to oxygen. Towards oxygen. Here we see that there is a net dipole. Kasi yung dalawang dipoles na yan, papunta kay oxygen, guys, di yan magka-cancel, okay? Again, papunta kay oxygen. That's why may net resultant dipole na nag-form. And also, we see that there are two lone pairs on oxygen. This also contributes to the distortion of charges between hydrogen and oxygen. And this contributes to the net dipole of water. Thus, water molecule is polar. Okay? Now, we have a sample problem. Determine the molecular geometry and polarity of CH4 methane. Okay, pause this first and try to answer. Okay, guys, now let's answer. As you know, dapat alam natin that this is the Lewis structure for methane. It has 4 bond pairs. Thus, its molecular geometry is tetrahedral. Now, what can we say about its polarity? Guys, take note that tetrahedral molecules are highly symmetric. Pero more than that, this molecule, okay, has CH bonds. Because it has CH bonds, methane is non-polar. Okay? Now, it is commonly assumed that the CH bond is non-polar because the electronegativity difference between carbon, which is my EN value na 2.5, is tapos, ang kay hydrogen naman 2.1. So, yung EN difference nila is minimal lang. Diba? 2.5 minus 2.1, 0.4 lang. And it does not result in significant bond polarity. Okay? Guys, tandaan ito, okay? Dahil this will be significant in compounds such as methane and other organic compounds that you will encounter in organic chem. So, lahat ng hydrocarbons meaning my C and H lang, so it consists of C and H only, they are all non-polar, okay? Because again, of the small electronegativity difference between C and H, okay? Now, let's proceed. We have a sample problem. Classify the following compounds as polar or non-polar. Ayan, guys. So, pause this video first and try to answer. Okay, let's answer. So, syempre guys, hindi ko nag-draw yung Lewis structure. Kayo na bahala, okay? Kayang-kaya nyo na yan. So, for BF3, boron trifluoride, the molecular geometry is trigonal planar. For methane, it's tetrahedral. For phosphorus pentafluoride, it's trigonal bipyramidal. For sulfur hexafluoride, it's octahedral. First, let's take a look at BF3. So, guys, boron is less electronegative than fluorine, right? So, yung dipole nyo papunta dito, okay? Tapos dito, and dito. Now, guys, makinig ha, yung dipole dito sa left and dipole dito sa right will have a resultant dipole going pababa. Ayan. Again, when you add this and this, it forms a total dipole papunta dito. Resultant dipole. And yung dipole dito sa baba will cancel out with the dipole sa taas. What can we say? We have a zero dipole moment for boron trifluoride. Wala siyang net dipole. Therefore, boron trifluoride is non-polar because it is highly symmetric. Next for CH4, guys, alam na natin na non-polar ito, diba? Again, not just because of the symmetry, but because we have CH bonds. Pero guys, tetrahedral molecules are also highly symmetric. That's why yung dipoles nila nagka-cancel out. Pero kay CH4, we know that it's non-polar because of the CH bonds. Next for phosphorus pentachloride. Okay, so mas electronegative si chlorine. So yung dipole papunta from phosphorus to chlorine. Okay, let's draw. Pag ganun. Okay, pag ganun. Hindi mabuti. Pag ganun. Tapos pagbaba. Now, guys, yung dipoles na ito, wait lang, change ng color. Dipoles na ito and ito will have a resultant dipole papunta dito sa gitna nila. Okay? Now, yung dipole dito sa taas will cancel out with the dipole sa baba. And the dipole na nasa left side will cancel out with the dipole na nasa right side, yung resultant dipole na naka-green. So, we have zero net dipole for phosphorus pentachloride. It is also highly symmetric because we can cancel out all dipoles. Thus, phosphorus pentachloride is non-polar. Lastly, we have sulfur hexafluoride. So, sulfur is less electronegative than fluorine. So, papunta kay fluorine ang dipole from sulfur. So, let's draw. Ganyan. Ganyan. Tapos, pag ganito. Ganyan. Okay? So, ito guys, yung ang dipole na ito and dipole na ito will result in a resultant dipole sa gitna nila. Then yung dipole nito and ang dipole nito will result in a resultant dipole dito sa gitna nila. Okay? So yung dipole sa taas will cancel out with the dipole sa baba. And the dipole sa left will cancel out with the dipole sa right. So sulfur hexafluoride is highly symmetric as well kasi lahat ng dipoles niya naka-cancel out. Since it has zero net dipole, sulfur hexafluoride is non-polar. Ayan. So zero net dipole meaning non-polar. Guys, anong napapansin natin sa lahat ng structures na ito? Lahat sila, number 1, walang lone pairs. Number 2, pare-parehas yung terminal atoms nila. For example, boron trifluoride, lahat fluorine yung terminal atoms. Si chlorine, hydrogen lahat ang terminal atoms. Si PCl5, chlorine lahat ang terminal atoms. Si sulfur, SF6, lahat fluorine ang terminal atoms. Okay? And lahat sila, puro made of single bond. Okay? So we can make a generalization. So, molecules without lone pairs are automatically non-polar given the following conditions. Number 1, terminal atoms are identical. For example, dito kay boron to lahat, boron. And number 2, all bonds have the same bond order. So we know, for BF3, lahat naman yung single bonds, diba? For CH4, lahat din single bonds. For PCl5, lahat din single bonds. Okay? For SF6, alam natin lahat single bonds. Okay? I hope that's clear, guys. Now, another sample problem. Please pause the video first. Okay, let's answer. Draw the Lewis structure of sulfur tetrafluoride. Classify as polar or non-polar. Guys, di ko na ito isa-isahin, okay? So this is the Lewis structure of SF4. And this is its 3D geometry. Now what can we say about its molecular geometry? It has 4 bond pairs and 1 lone pair. So AX4E1. So ang molecular geometry niya ay, ano kaya guys? Tama, seesaw. What about electron pair geometry? Ano kaya guys? Tama, trigonal, bipyramidal. Dahil it has 1, 2, 3, 4, 5 electron pairs. Okay? Now, let's find the polarity of SF4. So we know that sulfur is less electronegative than fluorine. So yung dipoles papunta kay fluorine. So let's do it. Dito, 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 papunta, dito. Okay. So guys, magka-cancel out to yung nasa left and right. Okay? Pero yung nasa gitna nito and nito, which is ito, hindi yan magka-cancel out. Okay? Again, itong nasa bottom na fluorines, yung dipoles nila hindi magka-cancel out. You have a net dipole. Okay? Also, the presence of the lone pair here makes the charge distribution sa molecule mas uneven. Kaya nagiging mas polar ang SF4. Kaya nagkakaroon siya ng net dipole. So 2 reasons why it has a net dipole. First, it is asymmetric kasi may net dipole siya na mapupunta dito. And second, it has lone pairs that will contribute to the uneven charge distribution around this molecule. Okay? Thus, SF4 is polar. Next, we have, okay, chlorine trifluoride. So we also solved this earlier. So this is the Lewis structure. Then we classify if it is polar or non-polar. First, determine natin yung molecular geometry niya. So we see that it has 3 bond pairs and 2 lone pairs. Thus, it has a T-shaped molecular geometry. Now, let's draw the dipoles. Okay? So, mas electronegative si fluorine. So, papunta sa kanya ang dipoles. Ganito, ganito, and ganito. Okay? You may think that this will cancel out with this one. Pero may net dipole pa tayo dito sa gitna. Okay? That's why ClF3 is polar. Also, guys, meron tayong presence ng, ano naman guys, lone pairs that will contribute to the uneven charge distribution around ClF3 molecule. Okay? So, the main reason, guys, bakit polar sa ClF3? First, dahil sa asymmetric shape niya. Kasi meron kang net dipole na napunta dito, right? And second is because of the lone pairs, which contributes to the charge distribution. Okay? Last, we have xenon tetrafluoride. Then classify it as polar or non-polar. Okay, ma'am, paano mo na ito i-draw kasi hindi ko gets? Okay, sige, para mas magets natin. So, total valence electrons, xenon has 8 valence electrons, diba? Because it's a noble gas, plus 7 times 4. That is 36 valence electrons. So, we know that fluorine is more electronegative than xenon because noble gases, guys, gaya ng sabi natin, they have lower electronegativities kasi they tend to not attract electrons anymore kasi filled na and complete ang valence shell ng xenon. So, let's draw. Okay, mabilisan lang. Then, I'll draw the lone pairs on the terminal atoms kasi alam naman natin na matik yung terminal atoms natin na si fluorine follows the octet rule. Okay? Now, so far, let's count how many total electrons we have on xenon tetrafluoride. We have 8, 16, 24, 32 valence electrons. Kulang tayo ng ilan, guys? 4 valence electrons, right? So, ilalagay natin yung 4 valence electrons na yun on the central atom. So, we add 2 lone pairs. Yan. So, let's check. We have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36 valence electrons. So, this is the correct structure of xenon tetrafluoride. Ayan. And this is the 3D geometry. Now, what can we say about its molecular geometry? It has 4 bond pairs and 2 lone pairs, AX4E2. Thus, its molecular geometry is square planar. Okay? Now, guys, let's draw the dipoles. So, papunta kay fluorine because, again, mas electronegative si fluorine. So, I'll draw. Okay, guys. So, kung papansinin nyo, ang dipole na ito will have a resultant dipole sa gitna. Ayan. Pag in-add up nyo silang dalawa, ito yung result nila. Then, pag in-add mo ito and ito yung resultant dipole nila. Now, this dipole sa left and this dipole sa right will cancel out, right? Tapos, ganun din yung 2 lone pairs mo nasa taas and nasa baba. It will cancel out. Okay? Thus, we can say that xenon tetrafluoride is non-polar. Bakit, guys? Because this molecule, specifically AX4E2 square planar molecules, they are highly symmetric. Okay? Meaning, lahat ng dipoles niya and lone pairs will cancel out. Okay? I hope that's clear. Now, another sample problem. O, kayang-kaya yan, guys. Okay? So, pause the video first and try to answer. Okay, let's answer. So, for bromine pentafluoride, guys, hindi ko na ito i-draw isa-isa, okay? So, this is the 3D geometry. For SF4, ito, ammonia, and sulfur dioxide. Okay, let's recall first. Bromine pentafluoride, it has how many bond pairs? 5 and 1 lone pair. So AX5E1, that corresponds to a square pyramidal molecular geometry. For sulfur tetrafluoride, again, it has a seesaw molecular geometry. For ammonia, it's trigonal pyramidal. And for sulfur dioxide, it's bent. Okay, so check natin isa-isa yung dipoles nila. So papunta kay fluorine for bromine pentafluoride. Okay, let's use the red one first. A minute. Ganyan. Papunta dito, 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 and then dito. Tapos may resultant dipole na naman ito plus ito papunta dito. Then yung sa left naman ganun din. So ito plus ito equals to the dipole papunta sa gitna dito. Okay. Now, yung dipole sa left and dipole sa right will cancel out. Pero you still have a net dipole here, yung papunta sa taas. Okay? And also, you have a lone pair here na nakakagulo sa charge distribution around the bromine pentafluoride. Again, bromine pentafluoride is asymmetric and it has a lone pair that unevens the charge distribution. That's why bromine pentafluoride is polar. Next, for sulfur tetrafluoride, we know that it is polar as we explained kanina. Next, let's explain ammonia. So for ammonia, papunta kay, kanino papunta guys? Siyempre kay nitrogen, okay? Ating dipoles. So here, there is no symmetry, right? Meron kang net dipole na ma-form kasi lahat ng dipoles mo papunta kay nitrogen, which is more electronegative. And also, you have a lone pair here na nakakagulo sa charge distribution in this molecule. And that's why ammonia is polar. It has a net dipole. Lastly, for sulfur dioxide, okay, so yung ating dipoles papunta kay oxygen because oxygen is more electronegative than sulfur. So, ganyan. And we have a lone pair here. Okay, guys, hindi magka-cancel out ang dalawang dipoles na ito. Okay? Kasi hindi sila symmetric with each other. Again, hindi sila symmetric with each other. In fact, gagawa pa nga sila ng resultant dipole papunta dito. Okay, so ito plus ito is equal to a dipole na papunta sa baba. Okay, and then we have a lone pair here that will just make the charge distribution around SO2 uneven. That's why SO2 is also polar. Diba? Sinasabi lang natin dito na pag may net dipole, polar ang molecule. Now notice guys na may lone pair sila lahat. Question, ma'am, does it mean pag may lone pair, polar na agad ang molecule? Guys, no, okay? Be careful in making generalizations. Not all molecules with lone pairs are polar because their presence alone is not the main cause of polarity. So lone pairs contribute to polarity by repelling the bond pairs, which distorts the molecular geometry and leads to asymmetry. So lone pairs, they also affect the electron distribution or the charge distribution within the molecule. Kaya, nagkakaroon tayo ng net dipole or non-zero dipole moment. Okay? So, the technique here is, alamin niyo muna ang correct geometry ng molecule and properly check if there is a net dipole. Huwag kayong mag-assume agad na porket may lone pair, polar. Okay? Hindi ganun. Okay? So, here, recap ulit ng summary of various types of molecular geometries, their examples, and now with the corresponding polarities of the example. So, for linear molecular geometry, our example is CO2, right? Which is non-polar. Because again, symmetric siya, so yung dipoles niya nagka-cancel out. So, for 3 total electron pairs, trigonal planar molecular geom, ang example natin ay DF3. And DF3 is non-polar because it is symmetric and lahat ng dipoles niya ay magka-cancel out. Next, okay, for bent molecular geometry, SO2, sulfur dioxide. Okay, so sulfur dioxide, as discussed kanina, is polar. Okay, because you have a net dipole. So ito plus ito equals itong nasa gitna. And you have a lone pair that will contribute to the uneven charge distribution around the SO2 molecule. That's why SO2 is polar. Next we have, so tetrahedral methane, we know that it is non-polar. For trigonal pyramidal ammonia, we know that it is polar because it has a net dipole na papunta kay nitrogen. Okay, again guys, this is the correct Lewis structure for ammonia, okay? And for water, we know that it is also polar, okay, because it has a net dipole. Next, we have the trigonal bipyramidal molecular geometry. Our example is phosphorus pentachloride, and we know that it is non-polar because again, the dipoles cancel out. Next, for seesaw molecular geometry, we have the example SF4, when we know it's polar kasi may net dipole. Guys, asymmetric ang shape niya. Okay, that's why hindi maka-cancel out ang dipoles niya. Okay, and dahil din sa presence ng lone pairs na nag-uneven sa charge distribution. Second, next we have E-shaped molecular geometry. So our example here is BRF3. Again, guys, ito ang tamang drawing for BRF3. Okay, may 2 lone pairs ka. Here again, BRF3 is polar because it is asymmetric and it has a net dipole. Next, okay, ito tingnan niyo guys, si linear AX2E3. Okay, so meron siyang 2 bond pairs and 3 lone pairs. Ang example natin is xenon difluoride. So it is actually non-polar. O, tingnan natin bakit. Again, the dipole goes to the more electronegative. So, papunta kay fluorine. Magka-cancel out yung dipole sa taas sa dipole sa baba. And magka-cancel out din yung lone pair sa taas sa lone pair sa baba. Okay? This is also a highly symmetric molecule. Okay? That's why AX2E3 linear such as XEF2 is non-polar. Okay? Wala siyang net dipole. Next, for octahedral molecular geometry, we have sulfur hexafluoride. Again, we said that it's non-polar due to the zero net dipole. Next, we have square pyramidal molecular geometry. And our example here is BRF5. So it is polar. Okay? Again, tingnan natin. BRF5, yung dipoles niya papunta dito, 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 and then dito. Tapos sa gitna ng dalawa nito, may net dipole ka sa left. Tapos dito, yung pag-i-add mo ito and ito, may net dipole ka dito. Okay, fine. Sige, pwede mag-cancel out itong sa left and sa right. Pero may net dipole ka pa rin dito papunta sa taas. Okay? And you have a lone pair. So BRF5 is polar. And lastly, XEF4, square planar siya na molecular geometry. It is non-polar again because it is highly symmetric. Hence, lahat ng dipoles niya and lone pairs niya will cancel out. Okay? I hope that's clear, guys. Ayan. So, done na tayo sa polarity. Now, let's proceed with intermolecular forces or IMFAs. So, intermolecular forces are the forces of attraction between molecules. Although weaker than intramolecular chemical bonds, they play a crucial role in determining the physical properties of substances, such as boiling point, solubility, and physical state. So these are the 4 main types of intermolecular forces, namely the London dispersion forces, which occurs in all molecules and is the weakest attraction, the dipole-dipole forces, which occurs between polar molecules with permanent dipoles, hydrogen bonding, and ion dipole forces. Okay guys, so Van der Waals forces is a general term used to define the attraction of intermolecular forces between molecules. Take note ha, these are the Van der Waals forces, London dispersion forces, dipole-dipole interactions, and hydrogen bonding. So ion dipole forces are not Van der Waals forces because the interactions occur between an ion and a polar molecule. So here we have some examples for dispersion forces. Okay, it usually occurs between 2 non-polar molecules. For example, iodine molecule, okay, forms dispersion forces with another iodine molecule. Next, dipole-dipole between polar molecules. We know that Hi is polar. So they will form dipole-dipole interactions because they are both polar. Now for hydrogen bonding, it occurs when the hydrogen atom is bonded to a highly electronegative atom such as NOF. So strictly NOF lang ang nagkakaroon ng hydrogen bonding, guys, okay? Hindi ko na ulitin yan. Again, si NOF lang. Nitrogen, oxygen, and fluorine. So the hydrogen from another water molecule will be bonded to another oxygen, which is more electronegative. And this comes from another water molecule, okay? Lastly, ion dipole. So we have a chlorine here, chloride and ion, that will interact with the partial positive charge of hydrogen here. And hydrogen comes from the polar molecule Hi, okay? And that is what we call ion dipole. So firstly, these are the London dispersion forces. In one side, there is a region of high electron density. Kaya sa region na yun, you will have a temporary partial negative charge, right? Now, on the opposite side, you have a region of low electron density. Kaya magkakaroon yung side na yun ng temporary partial positive charge. Now, this temporary dipole sa isang molecule, yung nasa right, can induce a dipole on the neighboring atom, yung nasa left, by distorting the molecule's electron cloud. So, the temporary partial positive region, to the right, will then be weakly attracted to the temporary partial negative charge of the left molecule. And that creates an instantaneous dipole. So, the big attraction between them is called the London dispersion forces. Second, so dipole-dipole interactions occur between polar molecules, where the partial negative charge of one polar molecule is attracted to the partial positive charge of another polar molecule. So these interactions arise from permanent dipoles, making them stronger than dispersion forces. Again guys, sa London dispersion forces kasi, temporary dipoles lang form instantaneous dipoles. Whereas sa dipole-dipole interactions, it's permanent dipoles. That's why it has stronger interactions. So substances with dipole-dipole interactions tend to have higher melting and boiling points and dissolve more easily in polar solvents. Now, one special type of dipole-dipole interactions is hydrogen bonding, where hydrogen is bonded to a highly electronegative atom, which is either nitrogen, oxygen, and fluorine. And it is attracted to a lone pair on another electronegative atom in a nearby molecule. So for example, we have a water molecule here. Okay. Now, ang hydrogen na ito is bonded to a highly electronegative atom. So sa lone pair, one of the lone pairs ni oxygen from another water molecule. Okay. That's what we call hydrogen bonding. Okay. So this is also called hydrogen bonding. Tingnan nyo guys. Ayan. Hydrogen bonding linya. Okay? This is also what we call hydrogen bonding. So substances with hydrogen bonds have higher boiling and melting points and dissolve more easily in polar solvents compared to those with only dipole-dipole interactions. Third is ion-dipole interactions, where an ion and a polar molecule interact with each other. So, as we said kanina, the negative charge of a chloride and ion interacts with the partial positive charge of a polar molecule. So this interaction may vary in strength depending on the size and charge of the ion, the magnitude of the dipole moment, and the size of the polar molecule. Okay? Now, ano ulit guys? Tama, is hydrogen bonds, specifically hydrogen bonding in water, where we see that H is bonded to one of the lone pairs of oxygen. Okay, so this is oxygen. So the strong intermolecular forces between water molecules due to hydrogen bonds play a crucial role in its unique properties. So, did you know? Ayan. As water, yung water as liquid, molecules move freely and form temporary hydrogen bonds that constantly break and reform. Whereas water as ice, molecules slow down and form a stable hexagonal structure held together by hydrogen bonds. So guys, mas ordered ito, diba? Ang water molecule when it is in its ice or solid form. Okay? Whereas as liquid form, the molecules of water move freely. Okay? And the hydrogen bonds temporarily break and reform constantly. Okay? Ayan. Now, this simulation shows how water turns into ice and the intermolecular forces occurring between the water molecules. Ayan, nakikita nyo, diba? From liquid, okay, yung water nagiging ice because it is becoming more ordered, diba? More ordered yung arrangement niya. Okay? And that's how water turns from liquid to ice. So, guys, take note of this. IMFAs, or intermolecular forces of attraction, are weaker than intramolecular forces. Okay? So, intramolecular forces natin are the ionic, covalent, and metallic bonds. So, intramolecular forces, they are stronger forces that hold atoms together in a single molecule or ionic unit. Again, mas weak si inter kaysa kay intra. Okay, so let's compare the types of intermolecular forces in increasing energy, meaning with the lowest to highest energy. Okay, so guys, when we say highest yung energy ng attraction, meaning mas mahirap i-break yung attraction. Pag low naman yung energy, meaning it takes only low energy to break the attraction. Okay, so the lowest energy is the London dispersion forces. Its basis of attraction is the temporary dipoles from fluctuating electron clouds. So it has a low energy of maximum 40 kilojoules per mole. So for example, we have two fluorine molecules. So guys, both of them are non-polar. Again guys, there are temporary partial positive charge and temporary partial negative charge na magkakaroon sa isang fluorine molecule, and that will induce a temporary dipole to another fluorine molecule. That's why an instantaneous dipole will be formed between them. Again, it involves temporary dipoles or temporary partial negative or partial positive charges between them. Okay? Next, we have the dipole-induced dipole. So that is between a polar molecule that distorts the electron cloud of a non-polar molecule. So greater yung energy niya compared to London dispersion forces. So mas mahirap siyang i-break slightly compared to London dispersion forces. An example is the attraction of a polar molecule HCl to Cl2, which is a non-polar molecule. Okay? So yung partial negative charge in the hydrochloric acid, okay, will induce a dipole in the chlorine atom in the Cl2 molecule. Kaya magkakaroon si chlorine dito sa Cl2 ng temporary partial positive charge. Again, the partial negative charge of chlorine in hydrochloric acid will induce a dipole in a non-polar molecule. So this creates a temporary partial positive charge and a temporary partial negative charge on the Cl2 molecule. Again, that's dipole-induced dipole. Next, we have ion-induced dipole. So this time, an ion distorts the electron cloud of a non-polar molecule. So its energy is slightly greater than dipole-induced dipole and London dispersion. An example of this is the attraction of the iron 2+ molecule to a non-polar oxygen molecule. So yung ion na ito will induce a dipole kay oxygen molecule, and that will create a temporary partial negative charge and temporary partial positive charge. So yung positive charge ng iron cation will be attracted to the temporary partial negative charge of the oxygen molecule. Next is the dipole-dipole interactions. It is the attraction between permanent dipoles, meaning two polar molecules. And its energy is greater than ion-induced dipole, dipole-induced dipole, and London dispersion forces. An example is the attraction between two hydrochloric acid molecules. So they are both polar. So again, the partial negative charge of chlorine will be attracted to the partial positive charge of hydrogen from another polar molecule. Next, we have hydrogen bonding. So it has a greater energy compared to the dipole-dipole interactions. Again, a hydrogen atom is bonded to another electronegative atom such as nitrogen, oxygen, or fluorine. So guys, any lang sa tatlong yan ha, bawal ng iba, either N or F lang. Okay? So this is a hydrogen bond. Yung mga dot dots niya. Lastly, with the strongest IMFA and with the highest energy, it's the ion-dipole interactions. So that is between an ion and a dipole. So that's between an ion and a polar molecule, gaya ng water. So the positive charge of the sodium cation will be attracted to the partial negative charge of oxygen here. Okay? And that is much greater than energy compared to hydrogen bonding, dipole-dipole, ion-induced dipole, dipole-induced dipole, and London dispersion forces. Okay? So from low to high energy. Thus, London dispersion forces has the weakest attraction, while ion dipole forces have the strongest attractions. Okay? And to summarize what we have learned in our chemical bound crash course, these are the types of the intramolecular forces. So, metallic bond, its basis of attraction is the positive metal ions, and the sea of the localized electrons na nag-iikot around the positive metal ions. And this is what it looks like. Okay? Next is the covalent bond, which involves the shared electron pairs between atoms. Okay, so again, sharing of electrons. Now, it has a greater energy compared to metallic bonds. So we can say that covalent bonds are stronger than metallic bonds. Lastly, ionic bonds are the strongest because it involves the electrostatic interaction between oppositely charged ions. It is much stronger than covalent and metallic bonds. That's why it has the greatest amount of energy needed to break these bonds. So here we have a cation and an anion. Okay. Ayan. Now guys, let's proceed to our general trends in intermolecular forces. Now, there are general trends in IMFAs because stronger forces between molecules mean they are harder to separate. So they boil or melt at higher temperatures. Now, bigger molecules na may larger molar mass, they have higher polarizability. Okay? Polarizability. Tandaan nyo to Which means, kapag ang isang molecule, malaki ang molar mass and high ang polarizability niya, mas marami siyang electrons that can move around more easily. Or yung outer electrons ng molecules na yun are less tightly held by the atom's nucleus. So dahil sa movement ng electrons na yun, they can form an instantaneous dipole or temporary dipole that, as explained kanina, result in dispersion forces between molecules. So guys, when comparing the IMFA strength or boiling or melting point of molecules, these are the factors that you must consider. So kunwari, you are comparing the boiling point, melting point, or di kaya IMFA strength ng dalawang molecules. Kunwari si molecule X and molecule molecule Y na lang. So, if they have a large difference in molar mass, yung dalawang ito, then ang dominating IMFA is dispersion forces. So when we say dominating IMFA, it is the type of IMFA that makes a molecule have a strong IMFA strength or high boiling point. So kunwari, sinabi na si molecule Y daw, okay, mas malaki yung molar mass niya compared kay molecule X. Okay? So we can say that molecule Y has a greater IMFA strength compared to molecule X. Or we can say that molecule Y has a higher boiling point than molecule X. And what if tinanong, ano yung reason bakit mas mataas yung boiling point niya? It's because of dispersion forces. Okay? I hope that's yan. Now, let's say naman, molecule X is non-polar. Tapos, molecule Y is polar. Tapos, guys, may mataas na difference or may malaking difference in their molar mass. Guys, ang i-consider pa rin natin is kung alin sa kanila ang may greater na molar mass. Okay? And ang dominating IMFA niyan ay dispersion forces. Okay? Next, what if guys, si molecule X na non-polar and molecule Y na polar, maliit yung difference na nila in molar mass. Let's say, around 0 to 3 grams per mole. Okay? Or let's say, same sila ng molar mass. Okay? Now guys, hindi na magdo-dominate si IMFA. Ang dominating IMFA ay ang dipole-dipole forces. So, between them, sino ang may greater IMFA strength? Siyempre, yung polar molecule Y. Okay? Again, bakit? Kasi, una, equal lang yung molar mass nila. Maliit lang ang difference nila yung molar mass. So, dispersion forces won't matter. And pangalawa, the dipole-dipole forces will dominate. Since polar si molecule, siya lang ang nagkakaroon ng dipole-dipole forces, hindi si non-polar. Si non-polar kasi, ano lang siya dispersion forces lang ang carry niya. Okay? And lastly, if, for example, si molecule Y naman, sige, palitan na natin, molecule A. Tapos, may hydrogen bonding ka dyan. Kumari, yan si water, ganun. Okay? So, automatic na guys, mas dominating ang hydrogen bonds kasi. So, si molecule A agad ang may greater na IMFA and higher boiling point due to the hydrogen bonds. Now, take note guys, that fluorine forms the strongest hydrogen bonds because among nitrogen, oxygen, and fluorine, okay, fluorine has the greatest electronegativity. Once again, dispersion forces are weaker than dipole-dipole forces. Okay? Then H bond is stronger than dipole-dipole forces. So, weaker to stronger IMFAs. Okay? Yes, guys. And lastly, the stronger the IMFA strength, the higher the boiling or melting point. Okay? I hope that's clear. Now, let's try to answer this sample problem. Okay, guys, so try nyo muna sagutan. So, okay, let's answer. Let's compare methyl fluoride and carbon tetrachloride, which has a higher boiling point. Ayan, meron na tayong comparison. We know, guys, that methyl fluoride ito is what? It's polar. Habang si carbon tetrachloride naman, it's non-polar. Okay? But let's compare using the table we showed kanina. Okay? So, in terms of molar mass, methyl fluoride, 32 grams per mole. Si carbon tetrachloride, 154 grams per mole. Again, methyl fluoride is polar, carbon tetrachloride is non-polar. Do they have a large or small difference in molar mass? Ano kayo guys? Yes, they have a very large difference in molar mass, guys. Specifically, mas mataas or mas greater ang molar mass ni carbon tetrachloride. Okay? And because of that, matik na, dispersion forces dominates. Okay? So, ang IMFAs involved in each of them, again, for methyl fluoride, LDF, and dipole-dipole. By carbon tetrachloride, LDF. Okay? Pero since malaki yung difference nila in molar mass, dispersion forces dominate. Thus, carbon tetrachloride has a higher boiling point compared to methyl fluoride. Okay? Guys, ganyan magsagot ng mga questions sa ganito. Tingnan nyo muna yung difference nila in molar mass. Hindi porket guys, na polar na si methyl fluoride, siya na yung sagot. Hindi, okay? Check first the difference in molar mass. Okay? Okay? So, as I said kanina, chlorine is larger and has more electrons. Kaya mas malaki yung molar mass ni carbon tetrachloride. So, as a result, the dispersion forces between carbon tetrachloride molecules are stronger, leading to a higher boiling point. Okay? Okay, sandaan ha? And keep in mind that dispersion forces exist among species of all types. Kahit may hydrogen bonding pa yan, may dispersion forces sila. Okay? Again, the greater the difference in molar mass, the more the dispersion forces dominate. Okay? Next, which has a higher boiling point, butane or acetone? Okay. Yeah, let's answer this together. So, butane, guys, is a non-polar molecule, right? But acetone is a polar molecule kasi meron pang carbonyl group, right, on acetone. Ito. Now let's compare their molar mass first. 58 grams per mole. Pareha sila ng molar mass. So there is a small difference in molar mass. Thus, the dipole-dipole forces dominate. Check natin IMFA sila. Si butane, London dispersion forces lang. Si acetone, London dispersion forces, and dipole-dipole interactions. That's why acetone has a higher boiling point because its dipole-dipole forces dominate. Or in other words, si acetone ang may higher boiling point because of its dipole-dipole forces. And pwede ko lang itong sabihin guys kasi equal or maliit lang ang difference nila in molar mass. Okay? Ayan. Again, the smaller difference in molar mass, meaning the dipole-dipole forces dominate. Okay? Next we have, which is a higher boiling point, bromine molecule or iodine monochloride. Okay, let's just answer together. So, si bromine molecule, it's nonpolar. Si iodine monochloride, it is nonpolar. It's polar because may electronegativity difference ka between iodine and chlorine. Okay, so you have dipole-dipole interactions if mag-interact siya with another iodine monochloride molecule. Okay, so the molar mass of bromine is 159.8 grams per mole. For iodine monochloride, it's 162.4 grams per mole. So yung difference nila in molar mass is 2.6 grams per mole. Sobrang liit yun guys. So they have a small difference in molar mass. Therefore, the dipole-dipole forces will dominate. Ang dipole-dipole forces ang i-consider natin kung alin ang may higher boiling point. Si bromine molecule, LDF lang ang meron siya, London dispersion forces. Si iodine monochloride, LDF and dipole-dipole interactions. That's why iodine monochloride has a greater boiling point than bromine molecule. Okay? Yeah. Guys, I hope that's clear. Again, you have to find the difference in molar mass first before determining alin ang may higher boiling point or higher melting point or stronger ion phase strength. Okay? Okay guys, kindly answer this first on your own. Arrange HF, water, ammonia, and CH4 in order of increasing boiling point. So pause this video first and try to answer. Okay guys, let's answer. So first, methane, it has the lowest boiling point kasi non-polar molecule siya. Hindi siya nag-exhibit ng hydrogen bonding because carbon is not a strongly electronegative element. Diba? Again, maliit ang EN difference between carbon and hydrogen. Kaya, London dispersion forces lamang ang meron siya. Meanwhile, water, okay, has the highest boiling point because it has 2 hydrogens and 2 lone pairs sa oxygen atom na mag-maximize ng formation of hydrogen bonds. So for example, we have a water molecule here, okay, and a water molecule here. Yan. So there are exactly the right numbers of hydrogen and lone pairs for every one of them to be involved in hydrogen bonding. Okay? For example, yung hydrogen dito, pwede mag-bond dito, dito, dito. Tapos hydrogen sa other molecule dito. Yan. Diba? And because of this, okay, water has a very ideal hydrogen bonding system. Next, ammonia naman has a lower boiling point compared to HF and water kasi iisang lone pair lang ang meron siya. Okay? Kaya yung hydrogen bonding niya ay limited. So for example, we have here a ammonia molecule. Okay? It only has 1 lone pair. Okay? Kaya yung tatlong hydrogen atoms on ammonia, okay, hindi sila completely makaka-participate in hydrogen bonding. Okay? For example, isang hydrogen lang ang kaya ng another ammonia molecule. Diba? Isa lang. So yung other 2, hindi sila makakapag-participate. Okay? That's why it has a lower boiling point. Now, HF, it also forms strong hydrogen bonds. Pero kasi guys, isang hydrogen lang ang nadodonate niya. Okay? So for example, this is the Lewis structure for HF. Okay? Since it only has 1 hydrogen donor, okay, hindi nagagamit lahat ng lone pairs na meron ang another HF molecule. Okay? Hindi nagagamit lahat. That's why this is the order in increasing boiling point. So from lowest to highest boiling point. So methane followed by ammonia, then HF, then water has a very high boiling point. Because again, it has a very ideal hydrogen bonded system. Okay? And guys, the greater the ion phase strength, the higher the boiling point. Okay? Now, intermolecular forces are also crucial in explaining properties such as melting point, conductivity, and the solubility in solids. This is because the IMFA strength of solids affects the packing of particles and their resistance to change. Okay? So we have 4 types. First, the metallic solids, okay, of course, made of metallic bonds. Now, their melting point is low to very high. And metallic solids are electrically conductive as a solid and in molten form, and they are insoluble in solvents, but they form alloys with other molten metals. So for example, sodium, magnesium, and aluminum. They are all types of metallic solids. Next, an ionic solid can have a moderate to very high melting point. Okay? Again, guys, ionic bonds are stronger than metallic bonds. However, ionic solids cannot conduct electricity in solid form, but ionic solids can conduct electricity in molten form and aqueous form. So they are soluble in water and polar solvents. For example, sodium chloride, magnesium oxide, and sodium nitrate. Covalent molecular solids have a low to moderate melting point, and they are generally not conductive of electricity in any form. So they are soluble in either nonpolar or polar solvents, depending on the molecule. So for example, nonpolar compounds such as helium and carbon dioxide, okay, or where helium, okay, it's mostly nonpolar, it is more soluble in nonpolar solvents. Pero yung mga polar molecules, for example, ammonia, okay, they are more soluble in polar solvents. So water is soluble in polar solvents. Diba? Kasi syempre, diba, water is also a polar solvent. Like dissolves light lang, okay? And lastly, covalent network solids have a very high melting point. That's why they cannot conduct electricity and they are insoluble in any solvent. Example is diamond, graphite, and silica. So here, this is an example of a copper metallic solid, sodium chloride ionic solid, sulfur covalent molecular solid, and diamond covalent network solid. Okay? Ayan. So guys, kita niyo sa diamond, naka-covalent network na, diba? And this is a very strong solid. That's why ang hirap niyan i-break. Okay? That's why it's insoluble in any solvent and it has a very high melting point. Okay? Now, sample problem. Solid camphor is insoluble in water, but is soluble in vegetable oil. The best explanation for the behavior is that camphor is A or an A ionic solid, B metallic solid, C covalent molecular solid, or D covalent network solid. Okay, so guys, this is what camphor looks like. Share ko lang guys, nagamit ko na ito sa lab sa previous job ko. Okay, wala, maganda yung amoy niya. Okay, so, ano kaya ang sagot guys? Okay, ang clue dyan guys is the vegetable oil. What is vegetable oil? Polar or non-polar? Tama, non-polar. So, most likely, covalent molecular solid ang sagot. Hindi pwedeng covalent network solid. Again, it's insoluble in any solvent. Okay? Pati na rin, C, metallic solid. Then ionic solid, it is soluble in water or polar solvent. So, hindi siya pwedeng sagot. Thus, the answer is C. So, CAM4 is a covalent molecular compound that exists as a crystalline solid at room temperature. It is used in products such as Vicks and efficacent oil for pain relief, headache, and coughs. Ayan, patapos na tayo, guys. Time for our pamasko Chloe cards, okay? So, answer. A molecule where electrons are shared unequally, causing one end to be slightly positive and the other slightly negative. Ano yun, guys? Tama, polar compound. Next, it is a type of IMFA that occurs in all molecules and has the weakest attraction. Yes, dispersion forces. It is considered as an ideal hydrogen bonded system. Water. Next, this type of solid is insoluble in solvents but forms alloys with other molten metals. Metallic solid. Next, this type of solid has a very high melting point and is insoluble in any solvent. Covalent network solid. Yay, we are done with Crash Course 5. Congratulations, guys. Now, time to answer Inorganic Chemistry Practice Test 5 for 20 minutes. Okay, guys. So, dito magtatapos yung ating crash courses for today. Congratulations for making it to the end of this video. Yay! Okay, so, last week, syempre, natapos na natin ang electronic structure of the atom, atomic properties, and nuclear chem. So, we also finished chemical bond and polarity and IMFAs today. So, for tomorrow, we will be having acids and bases. Okay? Then, guys, don't forget to attend our live PT discussion on June 15 for answering the questions of the practice test regarding chemical bonds, polarity and IMFAs, and acids and bases. Okay? Guys, if you have any questions at all, please do not hesitate to state it in the Google form, or you can always message me. Okay? Bye, guys, and see you soon.